Great. So we're going to kick off the last series of talks with Mike Biercuk from Sydney, and he's going to talk to us about quantum firmware and the role of quantum control in quantum computing.
So thank you, Krista, for the invitation to come and talk. This presentation is going to be a little bit different looking than the last few. I'm an experimentalist, so I'll talk at a higher level about some of the concepts that I wanted to convey about this idea of how quantum control plays into the way we design, or I think we might design quantum computers, but I'll also talk about some experimental results from our lab focused on the control of qubits realized in trapped ions. So very broadly, I'll follow this outline. I'll give just a little bit of motivation about why I think and why I argue that control and control engineering in particular will play an important role in designing quantum information systems. I'll give a tiny bit of background on the experimental platform we use, and then I'll talk about a couple of specific examples of the use of physical layer control for addressing problems like decoherence in quantum bits. Then one set of new results focused on how quantum control techniques can actually modify the effective error model experienced by real hardware to make it more compatible with higher level abstractions like quantum error correction. And I'll talk at the end about how some of these things actually have kind of a feedback loop in the design cycle on how you actually design and architect the quantum information processor. So for me personally, a lot of the inspiration for the kinds of work that my team pursues comes from lessons of past technology developments. And one example that I quite like, and I've presented this before, so some of you may have seen it, is the idea of looking back at the origin of flight. And so this image is obviously of the Wright brothers, who famously achieved the first manned-powered controlled flight. It's important to say that because at the time there was an entire aviation industry, and they were not the first to fly. They were the first to achieve this very specific goal in the field. And that goal was quite elusive for a long time, and it was elusive in part because there was conventional wisdom in the community. The conventional wisdom was that one would design an aircraft to achieve something called inherent stability. That effectively, no matter what the pilot did, the aircraft would keep flying in a stable way. And the goal of achieving inherent stability, I mean, it got the industry quite far, but eventually that was completely abandoned. And it was abandoned because of the developments that came in large part from the Wright brothers, who were bicycle engineers, and thought that instead of isolating the pilot from the system, that they should give quite a lot of control. And so I like this particular quote, which says, from the beginning, their goal was to devise a control system that would give them absolute command over the motion of a machine in every axis all the time. And if you're familiar with their particular prototypes, you know that what they did was they gave the pilot the ability to control the shape of the wing of the airfoil to the point where it was almost unflyable by anybody other than them. But this idea that control was an alternative approach to stabilizing an otherwise dynamically unstable system is now pervasive in engineering, and it's what shapes all modern aerospace engineering. So now let's think about how this comes into the idea of building quantum computers. I take this graphic from a paper by Cody Jones and Yoshi Yamamoto that gives one particular view of how to craft an abstraction or set of abstraction layers for designing a quantum computer. A lot of what we've heard about today comes at these top levels of the logical layer or the application layer. My talk is going to focus on these bottom layers, from the physical, the specific devices that we use that have quantum coherent effects, through the virtual, where we apply controls, and then up towards quantum error correction. And I'll start talking just a little bit about our physical system of choice. So, I mean, I'm an ion trapper. I had done a postdoc with Dave Wineland. Our preferred approach is to trap individual atoms. We do that using AMO techniques that are very common and have been around for many decades. This is a photograph of one of our experimental systems. This is an ultra-high vacuum chamber where we evacuate inside of that to about 10 to the minus 11 torr. And then what you can see right in the middle there is a set of 4 metal rods with a lens system above them, above those rods. Those rods are used to form a quadrupole potential. And so this makes what looks a little bit like a saddle by applying voltages of, you should think, 100 volts and something like 20 megahertz. When you make this saddle, the general concept is that if you were to put a ball on a saddle, it wants to roll down the concave down bit. But if you're able to spin the saddle at a rate fast compared to how quickly it can roll down the hill, you can achieve stable confinement. So with charged particles, we do the same thing using a kind of electromagnetic saddle. This so-called pseudopotential allows us to achieve stable charged particle confinement. Right? We trap ions in various different configurations. What you're looking at are photographs on a CCD camera of two different species. On the left, ytterbium, on the right, beryllium. In the linear Paul traps, like I told you about a moment ago, we trap things very similar to what you see on the left, from single ions down to small chains of ions. We have a whole separate program in my group that's focused on a very different kind of trapping technology called a penning trap, where we achieve stable confinement of large crystalline arrays of ions. This is a picture from when I was at NIST. What you see is that you can get this triangular lattice in a native way and have a spin 1/2 on each. So this is a nice platform for quantum simulation. For today's talk, I'm going to focus exclusively on this top left image, the idea of one ion as a quantum bit. And of course, if you're familiar with AMO physics, you know that our set of tricks focuses primarily on looking to the internal level structure of the atom as the source of a quantum coherent manifold. If this kind of diagram is not very familiar to you as an AMO physicist, it doesn't matter. All I'd like to do is call your attention to the fact that there are transitions in the optical near 370 nanometers that we can use here to cool our ions. And then there's a splitting in the ground state of the energy level structure that we use as a two-level manifold. This two-level manifold is our qubit. We assign 0 and 1 to it. It's near 12.6 gigahertz, which is very convenient because that's in the satellite communications band, and there's a ton of infrastructure that we can employ. And we can look to experimental expertise from NMR or EPR or general atomic physics developed over many decades to understand how to manipulate this two-level system. Importantly, that two-level manifold is differentially coupled to the optical field, such that if we are in one particular state, the one state here, we shine on the laser at 370 nanometers, it's bright, and we can take a picture of that. And if it's in the down state, we shine on the laser and we don't see anything. This is how we do projective measurement. So we have the ability to control the internal state of the ion using microwaves at 12.6 gig. We can read out optically and perform strong projective measurement. We can also do state initialization. Now, while I won't talk about it today, it's also very nice that in addition to the internal degrees of freedom, we also have access to external or extrinsic degrees of freedom, in particular the modes of motion of the ions. They're kind of like marbles in a bowl that slosh back and forth. Those modes of motion can be described as quantum harmonic oscillators. We can control those quantum mechanical harmonic oscillators in order to achieve coupling between the spin degree of freedom or the effective spin on these ions, and that's how we perform 2-qubit gates. I'm not going to talk about that today, but it's important in the context because you can go through some of the metrics associated with how well ions perform. They're actually quite nice in a variety of ways, and you can argue, of course, but I would say that they're probably the leading technology in terms of development. If nothing else, they've been around as quantum bits in that particular sense for a very long time. The kind of lifetimes we achieve are very routinely of order several seconds. If you try hard, Ki-Wan Kim just did a 10-minute experiment, but things like that had been demonstrated back in the 1980s as well. The effective energy relaxation time is something immeasurably long because of selection rules that prevent decays. The way we do these operations on the qubits using, in our case, microwaves, give us very high operational fidelity. So infidelities about 5 by 10 to the minus 5, measured by a couple of different techniques. 2-qubit gate fidelities in the 99.3 to 99.9% range, achieved by groups like Innsbruck. Gate durations of order 10 microseconds. Processors that are up to typically about 20 ions. That's what Chris Monroe and IonQ are using. It's also what the Innsbruck team has been using. Fully controlled 20-qubit coherent processors. IonQ is targeting 49 in 2018, from what I understand. So all the sizes are quite competitive. One thing that's really quite nice is the fact that the architecture has what you might call reprogrammable connectivity, you can achieve anything from kind of nearest neighbor pairwise interactions through to all fully connected graphs in a reconfigurable approach. I've heard Dave Moehring from IonQ, maybe at my prompting, now start to refer to this as a quantum FPGA, the idea that you can reprogram the connectivity in the architecture on the fly. Now, it's all very nice. It's a little bit of advertising for the community, but the important message is that as good as they are, they're not good enough. And I think that's a message that everybody here would appreciate. The question is, what can we do to improve them aside from making a better microwave system or the hardware improvements that will continue irrespective of anything else? So now I want to step up from the physical layer to this so-called virtual layer, where we talk about control and how control can be deployed to address this specific problem. How can we improve the performance of quantum hardware using control? The specific example that I like here is one that's very familiar in computer engineering. This is a cross-section micrograph of DRAM. And if you're familiar with DRAM, you'll know that each cell, each storage bit, is composed of one capacitor and one transistor. And if you write charge onto the capacitor, it's a 1. If there's no charge, it's a 0. Something quite remarkable about DRAM is that at some point in the past, a decision was made by people I don't know, and I don't know how this happened. I would love, if any of you actually know the story behind this, I'd love to hear it. But it was about a problem that they had in engineering DRAM. The problem is that the capacitors are leaky. And over time, when you put charge into the capacitors, it gradually just leaks into the substrate. It's kind of like having a bucket with lots of holes in it. The decision that was made that I think was quite profound was to say, well, we can try to patch the bucket, we can try to make it not leaky, or we can give up on that, because that's a hardware solution that can be quite costly, and just say, if we just refill the bucket every once in a while, we can keep it full. And so this led to DRAM refresh. So whether you are familiar with it or not, roughly at a kilohertz rate, so once per millisecond, all the DRAM in your computer, all the cells are refreshed. There's a voltage strobe, all the ones get refilled with charge, and the zeros stay empty. Right? This was a decision that, in my view as only a user and novice in the technology, was quite remarkable in driving DRAM to this highly commoditized product. It took what could have been a huge semiconductor development effort and turned it into a control effort where the control was all in software effectively. So how does a control engineer look at this kind of problem? And how do we think about it in our system, in qubits, right? We know that qubits are impacted by their environments. It leads to decoherence. This is a big motivation for a lot of the Microsoft efforts in topological qubits, in Majoranas. What a control engineer would typically do at a high level is write down something like this. This is called a block diagram, where we talk about the plant. That's the thing we want to control. For us, it's, say, a qubit. There's a controller that acts on it. Maybe there's some sensor and some feedback loop. What's really nice about this kind of approach is that you've completely abstracted away the microscopic nature of whatever the physical system is. And with this kind of block diagram, there are just rules that tells you how a given input maps to a given output. You don't have to go through all the first principles calculations in, say, the time domain. You just know that the output state is related to the input state by this thing called a transfer function, which is the forward path over 1 plus the product of the forward and the return path. There are rules about this. And it makes it extremely powerful. And that's what I would argue is what has allowed us to achieve really tremendous things in systems integration and systems engineering. What we want to do is see what lessons can be learned and ported to the case of controlling quantum bits, where many of the rules are different. We know that measurement is very costly because it destroys quantum coherence and the like. So what I'll focus on in this talk, although our group does work in all parts, is this top part of the diagram, forgetting the feedback loop, and achieving what's called open loop control. That is measurement-free control. DRAM refresh is an example of open loop control. The strobe just happens once a millisecond. It doesn't measure if the cells are empty or full. So if we quantize this just a little bit, we can think about some input state, some output state, as here a function of time, where your qubit is now going to be subjected to some stochastic process described by its spectral properties. And you can perform via the controller some set of time domain operations of SU2. So they could be Clifford operations or the like. And let's just call that a quantum circuit here composed of some arbitrary set of Cliffords. What we want is something like that transfer function framework that I told you about before that allows this block diagrammatic approach to systems engineering and classical technology. It has not existed in quantum technology in the same way for these nonlinear systems. Qubits are nonlinear, which makes this a very challenging problem in lots of respects. But my group has focused on this quite a lot. And you can understand some of the complication if you say, well, my output state here at time t is just the time evolution operator on psi of 0. Fine, you write that as the exponentiated Hamiltonian operator, where the Hamiltonian can be a time-varying quantity. Then you realize that there's the part of the Hamiltonian that describes your control, and then the part that describes whatever your environment is. And then you realize that the noise and the control may well not commute, right? So you could have sigma x terms and sigma z terms simultaneously. This becomes very challenging, certainly in the time domain. And so what we worked on was bringing this as a transfer function into the Fourier domain, where we tried to write down, and we eventually achieved, the ability to write this thing f of omega, the transfer function which describes arbitrary control. It describes it in the Fourier domain. The nice thing is that for arbitrary piecewise constant control, it can be very complicated control profiles in time. We can write down the transfer function, capture all the issues of non-commutativity of these different Hamiltonian terms. And we then use those in order to craft controls that are suitable for what we want to achieve. What's particularly nice about that is that it takes a complicated calculation of what do I expect my measurement, my error to be in a particular operation, and it turns it into a kind of simple heuristic argument. The heuristic is that the amount of error I have in this particular formalism is just given by that filter transfer function, which I can calculate for arbitrary control, and the spectrum of the noise, right? Just that overlap integral is enough to know, in this case to first order, what's going on here. Which means that you can think of, if you craft that thing in the right way, you can think of it like a filter. So I have some noise described by a spectrum. My qubit is subjected to it, but then I apply the right control to my qubit that effectively filters it, and I change the effective spectrum. For instance, I reduce the low frequency content. In general, these controls they behave like high-pass filters. They suppress low frequency things. The underlying physics, of course, is the physics of coherent averaging. This is something that we call dynamic error suppression. And it's very powerful. It's broadly used in our community. This is just an example from quite a number of years ago already, where we're applying two different control protocols on trapped ions. We're looking at how well our state is preserved. If the graph is on the low side of things, that's good. That's low error probability. As you add more control operations, the lifetime of the state improves, right? That's fine. The important thing is that the overlaid lines are not fits. They have, well, sorry, these are fits. They have one free parameter which rescales this noise spectrum, which we measure classically with the spectrum analyzer. These were magnetic field fluctuations in the lab. You see they agree quite nicely, and in particular, the presence of that one spur near 53 hertz that came from, 153 hertz, which came from a water chiller 3 labs down the hall, is entirely responsible for the bumps and wiggles that you see at these intermediate times, right? So you really do gain predictive control at a very fine level of detail by writing down these transfer functions, even for reasonably complex control protocols. And of course, you can suppress errors and extend lifetimes. I wanted to say very briefly that this is something that we've looked at outside of our qubit architecture. We've done some calculations looking at Majorana devices where you believe you'll be susceptible to classical voltage fluctuations. You know, these are things defined in semiconductor, superconductor hybrid systems. There are voltages around, and despite exponential suppression in variations in this sigma z term associated with the separation of the Majoranas on a particular island in this nanowire configuration, jitter in that can still cause problems. And we showed that using the filter transfer function techniques, we could calculate approximately for kind of realistic noise voltage causing jitter on those things, what kind of error rates we would expect for, in this case, the T-gate, like we heard before. And we could get factors of about 100 to 1,000 improvement by using dynamically corrected gate synthesis approaches, which just involve moving the Majoranas in a particular pattern, right? You can also suppress the sigma x terms if you do the right thing. The point, of course, is that if you can make a better primitive T-gate and then feed it into a magic state distillation, the amount of overhead required in the distillation will be reduced. It's the same argument as reducing error rates for quantum error correction. We've done quite a lot of work in this field. I just wanted to point out that Ken and I have done work in this looking at applying these same techniques to gain new understanding about composite pulses from NMR and answering some fun questions from that community as well. Now I wanted to take one kind of half step up and look at this intersection of the virtual and quantum error correction layers here, where the motivation comes from the collaboration I have with Rainer Blatt's team as part of the Equal Consortium, the Encoded Qubit Alive team, where our effort is focused on bringing control engineering expertise into the effort to build a logical qubit. The important concept is that the fundamental assumptions that make quantum error correction work are incompatible with realistic laboratories, right? The idea that all errors are independent and identically distributed is just not reality, right? It's mathematically convenient, I understand that, but instead we have correlations in space and time. One kind of correlation is just that the noise can exhibit temporal correlations. Here is a totally contrived numeric example where I show some noise that has some block correlation length. What happens, of course, is that the correlations in the noise are translated to correlations in the error in those underlying gates. So this is just a calculation that you can do for an arbitrary, randomly compiled unitary that ultimately implements the identity. You can calculate what is this error vector. So these are unitary coherent errors. They're not, it's not a depolarizing channel or anything like that, with this block correlated noise, and you look at what is the magnitude of that error operator, if you will, and you can calculate the autocorrelation, and you see as the noise correlation grows, obviously the error correlation grows. There's nothing surprising here, but this is a challenge because this violates the underlying assumptions of QEC in some way. We want to understand what exactly is going on and measure these correlations and then see if there's anything we can do about it. The big challenge, of course, is that we can only measure at the end of the circuit, right? That's something that everybody understands, I think. The insight into how to achieve this comes from just measurement science, from metrology. This is a totally random numeric example. I just generated noise in MATLAB or whatever. The important idea is that if you have a process that has some variance of its outcomes, if you averaging reduces the variance, right? So as you go from the black data to the red data, which are just averaged in a moving sense, the variance narrows from the black to the red. That's something that I think is familiar to most of us. This, however, assumes that all of those measurement outcomes are uncorrelated, that this is a white spectrum. If instead you do something really simple that's familiar from the clock community, like you add a linear drift term, then the same averaging has a very small impact on the measured variance of outcomes. This is very familiar if you look at Allen variance in clocks or anything like that. So we asked, can we do something simple? What can we average over? And for us, we can average over randomly compiled circuits that implement the same net unitary. So here what I'm showing is a set of experiments where we measure the fidelities, or the error, of different circuits that all implement the identity with two different noise processes applied. One with uncorrelated noise, so fast fluctuating, and the other with strongly correlated noise. Now there's quite a lot of work that goes into understanding the shape of these distributions. It comes from randomized benchmarking, and I'm happy to answer questions. But really the question here is, how does that variance, that width, change as a function of averaging over noise? And what you can see is that if you start with this correlated noise, as a function of averaging over engineered applied noise, again experiments, you see that the variance, it may fluctuate around, but it saturates at some fixed level, which we can actually calculate analytically. But in the case of the uncorrelated noise, it averages down approximately like 1 over n. And the curvature and things are things that we understand via some work with Tom Stace. This is the difference between the first crazy colored graph I showed and the second, right? The idea of this correlation leading to a saturation in the variance. Remember, oh, that's unfortunate. Matt? Anybody see that? Where are we? Sorry. Actually, I'm not going to apologize. Okay, so let's remember now this idea that the dynamic error suppression approaches act like filters, and they can suppress low frequency noise. If you end up with a noise spectrum that looks whiter at the end than when you started, you've made the error spectrum less correlated. And so now let's go back. This is the same graph I just showed you, and on the right, instead, I'm always applying strongly correlated noise, except I've replaced all of the gates in my circuit on the blue line with dynamically corrected gates. And you see that the scaling looks as if the error model has been transformed from strongly correlated to effectively uncorrelated to within the limits of the measurement by the action of the dynamical decoupling or dynamic error suppression approaches. This to me is really powerful because it says that instead of worrying about coming up with totally new quantum error correction protocols or having much nastier fault tolerance thresholds, by adding control, you can map the error model to one that is more mathematically convenient for QEC. Now, just at the end here, for the last couple of minutes, I wanted to address how all of these things can be linked together by thinking about control. Because what I haven't told you about is what the control should look like. In principle, you can do really crazy looking things with your control. You have, in our case, full control in time with reasonably high bandwidth over the amplitude, the frequency, the phase of your control fields. That's effectively infinite freedom. It's both a difficult optimization problem, which brings with it something called a lack of model robustness, that if the parameters against which you're optimizing change a little bit, everything breaks. But it also becomes extremely demanding on the classical hardware that has to implement this stuff. And the question is, can we be a little bit more clever? And can that feed back with the architecture of the system? Well, the approach that we take looks at these mathematical functions called the Walsh functions. They're square wave analogs of the sines and cosines. And going back to a number of projects we've done in my group, we've learned that the Walsh functions allow us to craft controls that are not only, in some cases, unique solutions to modulation patterns for dynamically corrected non-trivial operations or give you the timing for dynamic decoupling pulses, but also actually encompass almost all of the techniques developed in both NMR and EPR and quantum information through completely ad hoc and totally different physical mechanisms. Walsh modulation encompasses almost all of them, which is beautiful because now you have a single mathematical framework. In addition, I think it's beautiful because of the nature of these functions as bi-valued square waves. Now, I'll tell you more about that in just a second, but it's worth pointing out that there's been a lot of activity in this field. The black things are from my group, but we've also seen recently the extension of the use of these Walsh functions for constructing unitaries. For instance, Krista's group and Alana Spuru have both worked in this. There's a whole range of things that can be done with Walsh functions. They're obviously very well known in classical electrical engineering. It's very exciting to me to apply them in this different context. That excitement really comes from the fact that they have a really tight link to digital hardware. The Walsh functions have this beautiful representation that in the so-called Paley ordering, the Lth Walsh function can be written as a product or a mod 2 sum of square waves, of clocks that are easy to generate in digital hardware. So if you write out L in binary, every time there's a 1, you add the appropriate Rademacher. So if it's Walsh 12, it's 1100, you add R3 and R2 and you get that function. That's great because that's something that we can do in an FPGA extremely easily, right? So this is an example of using lookup tables with very low bandwidth overhead. We can craft the Walsh functions in real time. We can then extend that to make full-fledged controllers in the Walsh basis where we apply Walsh timing. We have Walsh modulated continuous output waveforms from a D to A, all in FPGA with improvements of over 100,000 times in the required resources or in latency to reprogram dynamically. This is a circumstance, it's just a toy demonstration, but it's a circumstance in which having some knowledge of the underlying physical system and the physics of the quantum control can allow you to architect controllers that are far more efficient. And this is a great way, in my view, to save on resources. So I'll just quickly summarize that we've talked a little bit about the importance of physical layer control for quantum information from the physical qubit improvement through to its impact on quantum error correction. We've talked a little bit about how this classical quantum interface can be improved using the physics of quantum control. We do a lot of other things like machine learning for predictive control and clocks and quantum simulation. I'm happy to chat with anybody who's interested, but I'll just, at this point, acknowledge my group and thank all of you for your attention.
Great, thank you, Mike. Are there questions for Mike? Great.
So I have one question about the use of wall functions. It's kind of looks all very nice that, you know, when you do digital stuff, you actually have this nice step functions, but this is not what happens in real life, right?
Sure, but it doesn't matter, which is quite amazing. So what you see here, it's a great question, and it's like, you know, what is the first referee criticism of these things? What you find is that it doesn't matter what the underlying nature of your pulsar is, right? So the idea is in the architecture, you separate the generation of your high spectral purity carrier, like a 12.6, from whatever does the modulation. So each segment in this gate, so this is a gate that applies a pi rotation of the qubit, right, a bit flip. Each segment is a Gaussian. It can be square, or it can be a Gaussian. And that's easy to engineer in anything. But Walsh synthesis then just tells you what the amplitude, the relative amplitudes of those Gaussian segments have to be. You can replace them with trapezoidal functions. You can replace them with anything. The optimization values of what the Walsh synthesis will be will change, but you can still always synthesize in Walsh functions.
Is this basically just a convenient way of representing when you like turn on some switches on for your carrier, basically, or should it be understood this way?
So this it would be like the I and Q waveforms that you spit out from a D to A that modulate the amplitude of your pulses.
Okay, thanks.
Are there any other questions for Mike? No? If not, let's thank Mike again for a great talk. And now we're going to hear from Matthias Schrodinger, and he's going to speak about whether or not AIs can dream of Schrodinger cats.
Yeah. So that work was done mostly by my postdoc Giuseppe De Calio, who about a year and a half ago asked me whether AIs can do quantum physics and whether that can be better or not than what we do normally. And I told him, okay, well, there's a big hype in AI, so yes, it's worth trying, definitely. However, I honestly do not believe that just taking a Boltzmann machine and thinking it can know quantum many-body states much better than things we've worked on for decades to optimize is a bit naive. AIs just cannot be that good. But in the meantime, I've learned a bit more about AI, and so I think I should not have been so skeptical, because as we've seen, this is the edge of AI this week, and it seems that simple neural networks, as I'll show you, can be amazingly good at learning quantum physics. What we think is hard, it may not be as hard if you just let an AI learn it. So they must somehow dream about Schrödinger's cat. What we want to solve here is not self-driving cars or whatever, but we want to solve the quantum many-body problem. We start with the Hamiltonians, electrons, atoms, spin, with some couplings between them. And then we want to solve either the eigenproblem and find the ground state, or we want to solve dynamics. If we want to do that exactly, then we start in a basis, and we look at the amplitudes in those basis states. For example, for the spin models, these can be the eigenstates of the spins. And I want to look at the amplitudes of each of the eigenstates. So I have to write down the wave function. That takes exponential with the memory, and we cannot go beyond about 100 spins or so, even if you turn the whole Earth into a computer. But we can do millions of spins. I've done 16 million spins decades ago with quantum Monte Carlo sampling. We can turn the quantum system into a path integral in imaginary time. We sample the paths, and as long as the model is stochastic, that means as long as the weights are positive, this works very well, and we sample the efficient, and we sample the relevant states. So though there are many states, the ones that contribute are smaller, and if we sample from them, that's good enough. We don't have to look at all states, we can just sample. We can also look at matrix product states. That's a compact representation of states instead of exponentially many coefficients. I write the wave function for some values of spin sigma IC to sigma NC as the product of matrices. So that's a compact sparse representation that works extremely well in 1D systems or a few coupled chains. So we have found lots of great representations in many cases, but they don't always work. Quantum Monte Carlo works as long as there's no sign problem. But when it's fermion, so when it's real-time dynamics, it breaks down. The matrix product states work well as long as the entanglement is low, so mostly in 1D systems, and for short time evolutions. To go further, we need new ideas. And now the question is, do we just have to think hard and we need just a brilliant graduate student to do it? Or can a machine just do it? Can we just have an AI that can translate languages, as we've seen, to automate tasks, drive cars, discover drugs, can also help us a little bit with physics? And that's what my postdoc, Dr. Giuseppe, wanted to try. And so the idea, or the way he describes what he wants to do is we look at the brain. And the brain is basically a function that takes some inputs into some outputs. I look at here, I see a face, I know it's Cresta, for example. And we just have to find the weights in the function that make this work. And that's what I learn, and we say, can this also learn a quantum system? Now this is as close to a brain as a spherical cow is to a real cow, but it's good enough. So AI is old. AI applied to quantum mechanics is what we've tried. And the idea is basically given a basis state. So given, for example, the C values of my quantum spins, I want to know what is the wave function. So basically, I want to learn the wave function. And I train the network to say if I have a spin that's up, 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 down, down, up, down, that it predicts the wave function value. That's what I want to learn. And when I look at that, then I'm skeptical, or I was. But basically, this is nothing but the variational wave function answers. We have some function that we want to optimize. And people have thought a lot about optimized Shastro many-body correlated wave function that are really finely tuned to it. Or similarly, the matrix product states are really finely tuned to 1D. There's lots of physics that goes into it. And now what Giuseppe said is, let us just use a restricted Boltzmann machine. So instead of putting in all of this quantum physics, let us just assume an Ising model on this graph. We have some Ising spins that correspond to the C values of my quantum spins. These are the visible spins, and I add another layer of hidden spins. These are extra classical Ising spins that describe that then should model all of the quantum mechanical nature of my quantum many-body state. And the more hidden then you have the variables I choose, the better the representation should become. The model then for the wave function in this restricted Boltzmann machine is simply the partition function of the Ising model. I have the hidden variables, the HIs, these are spins. I have the visible ones, the sigma ICs, which are basically clamp down, because for a certain value of those I want to know what is the wave function. And basically the wave function is the partition function of my Ising model given these specific values for the visible spins. And I want to learn the couplings in the Ising model, fields and couplings. And the more hidden variables I have, the more parameter, the better it may learn it. So then he first looked at the ground state. Yeah? We can just put in complex numbers here in the optimization. Learning complex, so here it's easy. Later, since here I just want to say with that answer, then I want to find the ground state, for example, I want to minimize the energy. The complex numbers get a bit more complex when I want to actually learn from a quantum experiment. Let's say somebody gives me a quantum computer with 1,000 qubits and want to learn the state. The way I do it there is I have to do measurements in various bases. I have to change the basis and measure in many phases, and that way I can then again learn also the phases. So for the ground state, I just choose some values of the parameters, and that is now just standard variational Monte Carlo methods, which my postdoc they worked on for a decade already. So that was standard. He just plugged in the RBM model. And so you start with some guess for the parameters. You calculate the energy. You want to then optimize it, find it better. You change parameters and so on until you find the best possible solution. The way one finds it, for example, is by looking at the energy and gradients. So I take an ansatz. I sample the system, I measure the energy, I measure the gradients, and then I do a step in stochastic gradient descent, and I slowly, hopefully, move towards the optimum. The way we get the gradients is we don't measure the gradients, so we don't sample it to different weights, but we analytically calculate the gradients, so the derivatives of the ansatz with respect to the parameters enter, and then I need to sample expectation values of those the gradient terms. These are basically the terms in the model, the ansatz and the energy. And that's what I sample, and then I take a step. And I got interested when he then showed me, this is a 1D Heisenberg model, length 40. He showed me that if he has 4 times more hidden layers than visible spins, if he assumes the model is translation invariant, so he just has 4n weights to adjust, then after doing about 100 iterations, the energy is converged to about 5 digits. within the noise. So it just perfectly gets the ground state of that 40-spin Heisenberg model with just 4 times more hidden layers. So it's not a big ansatz. When one then looks at models without the sign problem, where we can really know the ground state energy from QMC, like a 1D transverse field Filtninger-Eisinger model, length 100, the weight basically it goes down to tiny values in the errors with just 2 hidden layers. At the critical points, it's worse. Away from it, it's trivial. But it goes down exponentially in the number of hidden layers. For the Heisenberg model, 4 times more Ising spins than quantum spins. It's converged to about 5 digits already. For 2D, it's harder. There's much more to learn, but with about 8 times more Ising spins than quantum spins, this is the best available variational wave function that exists for the Heisenberg model. When I saw this, then I started being really interested, and I said, wow, these restricted Boltzmann machines seem to be really powerful for some reason that I don't yet understand, but they can learn quantum mechanics pretty well. What does it look like? No, so here I show the weights. First for a 1D the Ising model with 4 times more hidden spins than visible ones. And because I know the Hamiltonian is translation invariant, I make an ansatz that the weights are also translation invariant. And I now just show what is the weight of one spin in the center coupling to the neighbors. And these are the weights that it learned. So it seems to be quite short range. I think that's what we see, but also we don't really see much in what is the physics it's learned, and that's quite common in neural networks. We don't really see immediately what it learned, but just that it works. This is the Heisenberg model. It's much longer ranged. In 2D, we have here 16 times more spins, and we see they all learned some correlations, local. So there are all kind of correlations at certain distances it learns. A bit down, a bit to the right, a bit to the left, and so on. It would be nice now to understand that, to optimize it, to maybe guide it a bit, but it's learning correlations extremely well. Now, these are static properties for models that are stochastic. There's no sign problem. So these were test cases where we be new energies. We thought, okay, that may be easy. It would be great to now see, okay, let's go to more models. But first, we did something harder, namely we went to dynamics. That's when it gets hard immediately because the quantum Monte Carlo breaks down immediately. We can't do much. So here, what we want to do is we want to evolve the wave function in time. We write down the time evolution equation for a small time step. We write down the time evolution for the variational ansatz, assuming some time dependence of the weights. And then I want to choose those weights that this equation is as close as possible to that one here. And that I do by taking this one and that one. I take the inner products for the basis states. Then I get an equation that the derivatives of the parameters are then related to correlations between my operators and the energy. that I can just sample, and then I take a step. We've done that here for a 1D transverse field the Ising model and the 1D Heisenberg model where that we quench quickly, so it's highly non-equilibrium, and things work pretty well for times about 2 or 3 where it starts getting hard even for the DMRG calculations. So it works amazingly well also for dynamics. What we did recently is we said, okay, we don't just want to minimize the energy of a model. We don't just want to look at the time evolution, but can we learn a quantum state? So can this be useful for quantum state tomography? We said, okay, let us take a quantum system that we get from a quantum magnet, maybe, or from a quantum computer, and I want to learn the wave function. By measuring my qubits, building up a model, and then I want to predict properties of it. So I just want to measure the wave function, I sample, and based on that, I want to learn the representation. Now, when we did that, we did not have access to 100 qubits yet. So we said, okay, let's just take the thermal state, for example, of the transverse field the Ising model, or the Heisenberg model. We learned the wave functions, and then we looked at the correlation functions between I and j. This is the full one. This is the one that is reconstructed from the model we learned. And it works pretty well. We also thought, can one use that to calculate an entanglement the entropies, which are hard to measure? And the answer is yes, it works amazingly well. The solid points are the entanglement entropies that we calculated from the model we learned from local measurements. Here for the Isinger model, and here for the Heisenberg model. And it works, again, extremely well, which was surprising, at least to me. But that just means that I probably underestimated the power of AIs. Or I overestimated how smart we are in physics, that we know how to do things directly. So that has started the big industry. Now many people started to look into that, and I think as we build quantum computers, using the AI for learning about quantum states will become more and more important. I want to end by summarizing a few results by the other groups. Shankar Summers group and others showed that those states can represent the topological the states well. They can exactly describe the toric code state, for example, directly. It was also shown by that group that these states can represent states with the volume law entanglement, unlike the MPS states, which have area law. A Chinese group has shown that all of those states can be represented by MPS states, but the MPS states may need to have exponentially large bond dimensions. So it's sometimes exponentially better than an MPS states. And recently people showed also what can be represented with it. And it turns out that the RBMs can represent most interesting physical states well. There are some states that they can't really do well, but most interesting states can be learned by restricted, or can be represented by the restricted Boltzmann machine. The challenge will be, how can we learn it efficiently in all cases? Where do we want to go next? There's a lot that we can do. New states, tomography, ground state dynamics. We want to look into, can we use it to describe quantum circuits? So if, for example, Google comes and wants to show quantum supremacy with a circuit, the question is, can an AI actually learn these wave functions and represent it more efficiently to then see where is the real threshold for supremacy? And then there are many theoretical questions that one wants to look at. Thank you.
Thank you, Matthias. We have lots of time for questions, and we have a few, which is good.
Thanks, Matthias. That was a beautiful talk. I guess the question that comes to mind after that, what are they not good for, and does their excellent performance actually call into the utility of small-scale quantum simulators for a variety of problems?
Yeah, so what are they're not good for? That's exactly what we want to find out. For ground states, it works so well that I don't really know yet. I think we should look at states that are, we should look at highly frustrated ground states of models, competing phases to see whether there's a problem there. But right now, I think the question there is more, what interesting physics problems can we now finally solve with it, or can we try to solve? And that way, we will learn it. For dynamics, it's pretty good, but it's not perfect. After some time, things break down, which is expected because that's really hard. So I want to understand more kind of what is the limit of quantum dynamics and how far can it go there. Yeah, I want to find out the limit so that I know where it's actually good, and then I know exactly what to apply it for. Does it call into question the utility of quantum simulators? I think that was what we beautifully saw yesterday for those who were then the talk by Helmut Katzgraber, kind of the arms race we have between quantum simulators and classical machines. And what we've seen for quantum simulators, like quantum gases in the past, is that just trying to validate them or trying to match them or trying to beat them even led us to develop lots of new classical methods that really pushed the field forward. For example, for simulating the Hubbard model, that was around for 30 years. And we got stuck somewhere. We got stuck simply because we could not solve the high TC problem, which is kind of this holy grail out there. But with quantum simulators, we had easier goals. Can we solve the Hubbard model at higher temperatures than high TC, low temperatures? And there we made huge progress, for example, there. So I think that competition will rather trigger new developments and will help both the simulators by giving validation, and also the moment the results differ, that's where there's interesting science. So I think it's good for the field, and no matter what wins, because actually both methods will progress due to the competition. And we'll always need experiments to really trust what those methods calculate.
So I'm wondering how surprised I should be when I see results like this. Like, suppose that I know like the topological system is exactly described by PEPs.
Yeah.
Aren't PEPs like strict subsets of these tensor networks?
Yes. So there I wouldn't be surprised. It's nice to see the proof that it's possible, that it can encode the topological phase. Okay.
But
Nice.
same with all this 1D stuff, right? I mean, it should.
With the 1D stuff, I'm a bit more surprised because, okay, 1D stuff and MPS will work for sure, yeah?
Yeah.
When it's 1D local. What I was not sure is, if you now don't take this quantum mechanical wave function answers, but just the partition function of an Ising model, can that really learn this 1D quantum stuff, the correlations?
Yeah.
Yeah, so seeing that it works, I'm not as surprised in hindsight. But then in 2D, it was more, and I had this discussion, how can you be sure that it works in 2D and 3D? And because we have these long-range couplings, we're not local, so that's when it was no longer a surprise, because it's very easy to include long-range entanglement and correlations in the ansatz. So the power thing comes, so we simplify the model by going to a classical Ising model, but we give it more power by the long-range couplings.
And have you checked like if there's a like if you can make the Boltzmann machine like slightly more local and not lose any of
Those are interesting questions to look into. That I would love to look into, but right now we have to build a quantum computer. At least that's what Krista tells me.
Hi, Matthias. You have pointed out a larger, stronger expressive power of Boltzmann machines compared to tensor nets with bounded bond dimension.
MPS with bounded bond dimension.
Right. So one factor I'm aware of in this matter is the capacity of Boltzmann machines for capturing long-range entanglement in the data. Are you aware of other factors that would work towards explaining this separation?
I think that's the best argument I see. Yes, I know.
I just wanted to ask about how does the actual computation scale compared to, say, an MPS simulation or a PEP simulation as I grow the size of the system?
With Monte Carlo simulation, the scaling is typically linear in the volume, so it has very good scaling. Yeah.
That's for translationally invariant.
When it's translationally invariant, then it's even better than it's more like constant.
So Matthias, this connection between, say, n-dimensional quantum system and an n+1 dimensional, like the connection between an n-dimensional n-dimensional quantum system and n+1, backwards, and classical n+1 quantum works for translation invariant, at least Ising models, right? So I can always take a quantum Ising model and make it a classical Ising model in one more dimension.
Yes.
And then, do we have any rules for when I now make these graphs kind of partially non-local? It'd be nice if there was a map between, say, classical Ising models on graphs and Hamiltonians they represent. Does that exist? Anybody know?
I agree. It would be nice to have such a rule and understanding.
Utilizing the genus of the surface on which you're embedded. How many loops do you have to make phase in?
Great. So let's thank Matthias again for a great talk. And our final talk, last but not least, of the day is from Bettina Heim. She's going to tell us about service codes under optimal decoding.
Yeah, so good evening. I've got the responsibility of the last talk. I know you all want to go to dinner by now. So I thought it would be a good idea to go into some more depth so you can actually earn that dinner a bit. We've already heard a lot about quantum error correction, and because it seems likely that a lot of the architectures for quantum computing might have to rely on quantum error correction to actually get the necessarily fidelities to do practical applications, I will talk some more about error correction. Now, one of the candidates of how you could do that is always this idea of topological codes and topological systems. And the basic idea is quite simple. We want to encode the information we're interested in into something that is a little bit more stable. So we would like that our information is encoded into global degrees of freedom that are not easily changed by local perturbations. When we talk about error correction, usually these are active corrections that we will apply, at least in memory, to a system to get the state to what we want it to be. So in terms of this topological system, you could imagine that as being as excitations being quasi-particles that move around your system, and the task of error correction is to track their movement so that you can determine when accidental braiding has happened, which would change your logical state. Now, the topic of this particular talk, we already had a very interesting, some interesting facts by David on error correction, and I would like to pick up where he left off, which is the decoding part. And in particular, I would like to go into more detail rather than giving a good suggestion of how you might do this in the most efficient way. I would like to take a step back and think about what we would like to do ideally. If we could, what would be the optimal way or the best way to solve the problem? From there, we can see what consequences it has to make certain approximation, to make certain assumptions, to get to something more practical. So I realized that a lot of these quick introductions come a bit late in the day. I apologize. I didn't plan for the order. But I'll still briefly just introduce, because I know not quite everybody is familiar with the whole formalism, so just to go very quickly over it. So the one thing I'm going to be looking at in this talk are surface codes that you've heard a lot about already. And they belong to a particular family of error-correcting codes, which are stabilizer codes. The idea of this whole stabilizer formalism is to describe the system by a set of operators under which the state is invariant. So you get a group of operators that tell you what your system is going to look like, and what you would like to do is to do all your logical computations in their simultaneous +1 eigenspace. If we can achieve that, then the nice thing about that is that logical information is not changed if I apply any of those members. And I can actually detect local excitations by measuring with respect to the eigenbases of those operators. So let's look at a bit more concrete example. This tiny surface 17 code, why 17, you're going to see in a minute. We start out with 9 data qubits, and we're going to encode k logical qubits, which is in this case for the 9 qubits here, just 1 logical qubit. So the nice thing about surface code is that they're planar, and we've got rather simple checks. So our stabilizers in this case are simple Pauli operators, and they act only on 4 qubits simultaneously. So they're actually doable in current hardware. So what we do is some collective measurements to extract that, and these collective measurements are usually done in form of applying a short circuit onto those 4 qubits and an ancilla qubits to extract the value of the operator we are supposed to measure. Now, measuring the ancilla qubit will give us either +1 or -1, and will give us information about the location of our quasi-particles. The values that we measure are not unique to a certain error. So for example, if I have a particular error, a set error, on a qubit up there, I might just as well have an error up there and still get the same indication, the red marked ancilla qubits, to denote the error as by indicating it being -1 instead of +1 on measurement. So what the task of a decoder is to reconstruct the logical information that we encode into that system. By measuring these joint operators, we actually project the state back into the stabilizer state, and by eliminating the syndromes, we'll get it back to the code space. So the decoder is supposed to determine a correction based on these measured values, such that the final state is hopefully again the correct logical state we want to preserve. Now I told you we're going to extract the measurement values by applying a short circuit. This is the particular short circuit. So of course, since we apply a circuit, errors can occur during any time in the circuit and can propagate. So even though ideally we would simply like to measure some operations that gives us good information about how our system looks like, in reality these measurements are not necessarily correct. So if I have some error in between that circuit, that error will propagate, because I'm applying joint gates, to 2 errors at the end. And that's generally what we mean when we talk about circuit level noise. And the decoding I'm talking about actually is based on the complete noise model, so it takes every propagation into account. To do the best decoding that we can, it's very useful to think of errors in terms of a certain classification. So what we can do is say that we have a certain ideal syndrome that we would like to obtain. So when I have a set error on a certain qubit, there are 2 syndromes in this case that should pop up. That is basically the same as saying that assuming that the error would occur at the beginning of the syndrome extraction circuit. So any operation that eliminates these values will actually map the state back into the code space, though because it's not unique what errors might have occurred, the error pattern up here has the exact same syndrome as the one before, we do not necessarily get the correct logical state. If we apply the wrong correction, in a sense, we will have changed the logical state of our system. So in addition to classifying the state of our system according to the values that we measure, we also need to classify it according to a value denoting its logical state, its current logical state. In addition to that, we still have the assumption that error occurred right at the beginning of the measurement circuit, which is not the case. So it could have been anywhere during the circuit, which means that the values that we measured are not necessarily correct. So additionally to a logical operator, we also need to classify the state of our system according to the measured value of our syndrome. So to sum this up, we have some data qubits, we have some ancilla qubits, we have basically an ideal syndrome that classifies the state that our data qubits are currently in together with a logical operation. And we have the measured syndrome that classifies the state that our ancilla qubits are in. So that gives a complete description of our system. And that also means we end up with a whole bunch of equivalence class of errors. In general, we end up with a probability distribution of errors. So the system is completely described and all error propagation by a probability distribution across data qubits and syndrome qubits. So classifying that error actually allows us to completely describe all error propagation that occurs by a transition matrix that describes the transition from 1 of these cosets, of one set of errors reclassified into another one. Most of these entries of that matrix are actually 0, so we could describe it in terms of a smaller matrix that depends on the last measured syndrome and the next measured syndrome. Now, I admit that sounds all very technical, so what does that mean for our decoding? So the measured syndrome values give us our likely error location in a sense. But what we want to do is that we want to find out in which equivalence class of errors our current state is. So we would like to keep track of all error classes that we have. The issue with that is that there are a lot of them. In particular, we would have to recalculate basically the whole transition matrix for each part. When we do different logical operations, we would have to recalculate that transition matrix each time. Also, in general, if we have something more complex than polynoise, like amplitude damping, then it depends actually on the state of the system. So in reality, it's simply not doable to do that. To sum things up, it's an NP-hard problem to actually decode optimally. So what do we do? What we always do with NP-hard problems, well, we find some approximation to actually achieve the same thing without actually tracking all equivalence classes of errors. In the case of surface code, there's this minimum weight perfect matching, for example, that gives an efficient decoding in the sense that it's a polynomial time decoding. Now, polynomial time sounds nice, but again, it doesn't mean very much until you determine what polynomial exactly means. Now, it turns out it's approximately with code distance to the power of 4, I would argue. But it still seems like a bit much. So one might hope that there's a more efficient way, and the Reed scheme sounds really interesting in that direction. But the more interesting question to come from this perspective of what we would actually like to do is what kind of approximations make sense to do. Because we have this large joint probability distribution, our task, if we ever want to have to achieve an efficient decoding, is to split that distribution across all qubits into the product of smaller distributions. So how do we do that? Now, it is worth looking a bit into the kind of approximations that you could do, and it turns out it's quite practical to actually just use some min-weight perfect matching because it tends to neglect certain things of that distribution. So I'll compare some optimal decoded values with minimum weight perfect matching. To briefly tell you what it actually is that I'm talking about, you can think of minimum weight perfect matching as some sort of search algorithm that determines a suitable correction. So each measured syndrome change is interpreted as a vertex on a graph, and we assign weights between vertices. What we then try to do when we have certain values that pop up is that we always match them in pairs. That is very reasonable in case of the surface code because any X or Z error has to result in syndromes popping up in pairs, more or less. It's a bit less reasonable if you think of something like color code. So what you could do there is just project it down onto surface codes. But that's basically why this minimum weight perfect matching is somewhat specific to surface code because it relies on defects arising in pairs. And our goal, of course, is to minimize the total weight. Now, this kind of decoding is largely independent on the noise type of strength that we have, which is nice because we don't need to know anything about the noise that we have in our system. But one might also hope that if we did know what noise we had, we could use that information to do something better in the same time. So let's look at some assumptions. Let's look, for example, I talked about that we want to track equivalence classes of errors. So minimum weight perfect matching replaces this whole class by a representative in some way, by the element with the most weight. So in a sense, we are not, instead of looking for a minimum in free energy, we are looking for a minimum in energy. One might wonder if that's a reasonable approximation to make. that we can simply neglect entropic contributions. Another thing is that one might wonder what happens to different sorts of correlations, because these pairs, well, because you match pairs, the possibilities to actually match groups of syndromes is very limited. So if I have, for example, a Y error, I should not only have 2 syndromes that pop up, but in fact 4. Yet I'm still doing a matching of pairs always. I can adapt the weight based on some matchings, making it more likely to match sets when I previously matched X's on the same qubit. But still, that's already an improvement. So it's very easy to not do that and instead say, we're ignoring that completely, which means we would be ignoring some correlations of errors on the same qubit, the Y errors. We also largely ignore correlations between errors on different qubits, and these are much harder to account for when you set the weights. And what is most definitely ignored are correlations between faulty syndrome bits and faulty data qubits, because fundamentally we do a phenomenological decoding when we do min-way perfect matching. And I can't come up with a way around that, how you would adapt that. The algorithm is not designed to do that, basically. So the first thing people usually look at when talking about error-correcting codes and decoding is usually error thresholds. So some of you may have seen that plot. Basically, it's a reconstruction of an older paper from '09, where we get an error threshold that is roughly 1%. So maybe to clear up some confusion that might arise, because we heard numbers around 18%, I think, or even 39%. The 1% is if you actually look at the version where the measurements can be faulty. Then you end up with a much lower threshold than if you assume that all your measurements are perfect. So what even is an error threshold? So the reason we are that interested in that value is because below that threshold, the idea is that we can simply take more qubits and get a better logical qubit. So we can trade off physical qubits for reliability, in a sense, ideally. So this threshold depends on code, on decoder, and on noise type. The thing is, there are certain ways to determine it analytically, but not really for realistic error models and not for circuit level noise. You can make approximations for code capacity or even for phenomenological noise, but not if you actually consider a circuit. So correspondingly, we also have no idea what actually the best possible threshold is that we could achieve, which is kind of an interesting question. Now that one I can answer you pretty quickly. And it turns out, for this particular noise model, you wouldn't get over 1.8% no matter how you do your decoding. So the actual value that you see in the plot is a bit below that because it already does one approximation. It splits the decoding of the Z-type stabilizers and the X-type stabilizers simply because otherwise I needed around 140 gigabyte of memory. It seemed a bit much. So it split, and hence the estimate, but it looks like something around 1.5, 1.8%, which is great because that's definitely in the range that our physical qubits are currently. Good enough. So the noise model that these values refer to is more or less a depolarizing channel, but it has some correlations on CNOT gates. So each of the 2 qubit errors during the CNOT gates is equally likely. So in that sense, it's not an uncorrelated noise model, but a correlated one. And the good news is that there we actually do see the difference between a decoding that does not know anything about the noise model or the circuit and just blindly assumes nothing and applies a correction, compared to a decoding that has full information and uses all that information. But one might wonder that if there's no information that I could use, if there are no correlations that are interesting, we heard that it's, in some sense, it's easier to have correlations because it means you have information about your system. Now, if you don't have those, one might wonder if this perfect decoding is still better than simply blindly do a matching. Because in a sense, that's exactly the type of noise that minimum way perfect matching is perfect for. Now, the thing is, in a realistic setting, because we do have this little circuit to extract the syndromes, we're always going to have some correlations. So we look at an error model that, in a sense, is completely uncorrelated, in the sense that each error on each qubit is independent, but we still do the circuit, we still have some correlations because we propagate errors. We also switch from a 6-step circuit to an 8-step circuit, but these are minor adaptations. And what we end up with is definitely less of a difference between the two, but still visibly there's still a distinct difference between the two values. Now, if you look for minimum weight perfect matching, we can obviously get more data and actually look if the threshold, the observed threshold shifts as we actually go to larger code distances. And based on that, we would estimate that the threshold values are around 0.28% or 0.35% maximally, which is already a lot lower than before. So that's not quite an order of magnitude, but still it's a lot lower than the correlated noise model. So it seems reasonable that we should be using correlations. Actually, it seems reasonable to wish that we had a system that was in some way correlated to exploit that. But the question is, which correlations? Because they're also kind of hard to include in the decoding scheme. So let's switch to looking at how important different contributions could potentially be. Now, if we stick with min-way perfect matching, we had our more or less symmetric depolarizing channel. So in this case, it's actually a depolarizing channel. No correlations between C0 for errors on C0 gates. And if we compare that with the results for independent X and Z errors, there's absolutely no difference, which is not very surprising because, again, minimum way perfect matching doesn't make use of the information that there are correlations. It does the same thing for both noise models. Also, if you look at something slightly more complex, like a Pauli-Twirl approximation, which is still efficient, then you find that also here results match reasonably well. So it doesn't seem to make a huge difference if I have correlations between errors on the same qubit. Those do not seem to be very relevant in a sense, or very bad if we don't know about them. So one might wonder what happens if we have correlations between errors on different qubits that we don't know about, which seems like a realistic scenario. Approximation of an amplitude damping channel. Sorry, didn't know there were different ones. So one might wonder what happens if we have correlations between errors on different data qubits. And one simply one convenient way to actually generate interesting correlations is to take a really bad syndrome extraction circuit. So far, we've worked with this nice circuit that minimizes error propagation. Now, if we switch to something slightly differently, we're going to end up with something that is far less favorable for a decoder. Because instead of having error propagation in perpendicular to our logical operators, basically, that don't matter, we now have propagation in the direction that a single qubit error could potentially result in a logical error for a distance 3 code already. So if we take an extraction circuit like that, which basically results in a correlated noise model, we're going to see that that's already a lot harder to handle for something that doesn't know about that or doesn't use that information. On the other hand, if we stick with our perfect decoding, there's absolutely no sign of that behavior. Because we still do know perfectly well what our system does, it's in principle possible to perfectly account for those propagations and adapt accordingly. So that seems like one interesting thing to consider when we're constructing approximations. Because ultimately, once we get somewhere below threshold, what we're interested in is, or what has a large impact in orders of magnitude, is the asymptotic behavior. So it's an absolute waste to have a distance 10 code if our behavior actually, if the behavior of our code is like a distance 5 code, simply because we don't actually do a reasonable decoding. Another thing that I mentioned before is that, I mean, all these things, in principle, even for that syndrome extraction circuit, even with min-way perfect matching, there are ways to adapt. So as long as you know about those correlations, also with a matching algorithm, you could adapt your weights, and that behavior no longer occurs. The one thing that I told previously, what you can't really do, is account for correlations between syndrome qubits and data qubits. So the question is, are those having a major impact? So what we could do is to test that hypothesis is that instead of working with our probability distribution across our whole system, we could split that distribution into 2 parts, one for the data qubits and one for the syndrome qubits. So basically, we replace our models of all cosets there by distinctly less cosets, and additionally, simply a probability to have an error for the measurement. If we do that, surprisingly, there's actually still, it looks fairly well. The absolute value is slightly worse, but there's still a good asymptotic behavior. So it doesn't seem to have a significant impact on how our code for small error rates behaves, which is great. So what are the things we looked at and we found? So we looked at how important entropy contributions are, and we looked at how important different correlations are. We looked at, in particular, at the correlations between errors on the same qubit, between errors on different qubits, and between errors on syndrome and data qubits. Of those types of errors, what we really need to worry about are correlations between different qubits. So these are the correlations we do need to know about to some extent, and that need to be handled by the decoder in a reasonable way. The good news is that if we do that, we actually end up with a higher threshold than if we just had independent noise, or we were likely to end up with a higher threshold, which is great. So quick reminder for the threshold values. That's where we had it. It seems reasonable to do. And the results that are presented here, in some sense, give absolute upper bounds. There's literally no way to better decode. There are other noise models, certainly, that could potentially have higher thresholds. But apart from that, that's where we need to get. So what does that mean when we're thinking about moving to actual hardware? So the main issue is that it seems to me that there might be correlations we don't know about. Those are very problematic because it's very hard to design a blind decoder that behaves reasonable for all sorts of correlations. So to some extent, we do need to know what kind of correlations we should be expecting and we should adapt for. On the other hand, it's a trade-off between having to determine how your system behaves, which is expensive and hard to do and everything, and the gain that we actually get from it. So determining whether or not I have some Y correlations seems like a waste of time. But on one hand, there's in a sense, there's this trade-off between the classical and the quantum complexity. The more we know about our noise model, and the better we account for it, the less qubits we probably need to achieve the same results. Whereas if we don't do that, and if we just do a very fast but very crude decoding, we can take a larger distance code, but we might not end up with the performance that we would actually expect. So in a way, large distance code makes sense when we do have a reasonable decoder on one hand, but the decoder still needs to be fast enough to actually decode. So probably there's a sweet spot in between where we don't have huge code distances and not tiny ones that we can still process classically. As far as determining the noise model goes, it turns out knowing the structure of your noise, knowing which correlations occur, are fairly important, whereas knowing what actually your noise parameters are seems far, far less important. Now, the data wasn't shown, but actually modifying what probabilities our optimal decoder expects versus what probabilities it gets didn't change basically anything in the data. So for at least, these are very simple noise models that were tested, but at least for those, it seems to be less relevant to actually know the absolute values. What seems to be relevant is to know the relative values. What is more likely? What kind of structure we actually expect? And it also seems that it should be a very easy and straightforward thing to account for a syndrome extraction circuit. This is information we get for free, so we should use it. And even though for surface codes it's fairly easy to find a syndrome extraction circuit that doesn't propagate errors, and in that sense it's not needed to do that, there are other codes where you simply can't find this particularly nice way of extracting syndromes. So that's one thing we should look out for. So, and now I would like to thank my collaborators, and you've definitely deserved dinner.